You're listening to DTFHN for June 1st, 2026. I'm your warranty-voiding host, Jack Hacksman. We are your daily tech feed for Hacker News, a website where mass extinction events are debated with the same energy as tab wit. Today's a good day to own what you build and break what you're told you can't. Let's get into it. What does it actually mean for a technology to be accessible? We say it all the time. Democratizing AI, putting power in everyone's hands. But there's a version of that phrase that's mostly marketing. A company releases a model, hosts it on their servers, and charges you per token. You can use it. You can't own it. You can't run it in your basement on hardware you already paid for a decade ago. Is that access? Or is that a subscription to someone else's access? A developer writing on the point-free blog just ran Gemma 4, a 27 billion parameter model, on a recycled server with a 2016 Intel Xeon, 128 gigs of DDR3 RAM, and no GPU whatsoever. Not a modern workstation, not a cloud instance. A machine that by every reasonable benchmark has no business running a frontier language model. And here's where playing devil's advocate is instructive. You could argue this is pointless. The tokens per second are slow. The electricity costs over time might exceed just paying for API access. A pragmatist would say, use the cloud, it's faster, it's cheaper at scale. Stop romanticizing old iron. That argument sounds reasonable until you examine what it actually concedes. It concedes that you need permission. It concedes that someone else sets the price, the terms, the availability. It concedes that when the API changes, when the model gets deprecated, when the company pivots, you're out. The pragmatic argument for dependence is always compelling right up until the dependency breaks. What makes this post technically serious is the depth of optimization required. The author couldn't use Llama. It doesn't support the model architecture. And even if it did, it hides the performance levers you need on constrained hardware. Instead, they went directly to icom.cpp and manually tuned speculative decoding with NTP drafters, expert merging, flash attention, memory locking, runtime repacking. Every flag in that command line represents a decision about how data moves through a memory-bound system. The memory wall. The fact that processors spend most of their time waiting for weights to physically travel across the memory bus is the same bottleneck whether you're on a Xeon or an H100. The difference is that on commodity hardware, you can't brute force past it. You have to understand it. The comments from readers reinforce something the post implies but doesn't quite say outright. Multiple people are doing this. Someone's running the same model on a 2012 Xeon with 16 gigs of RAM, getting 8 to 12 tokens per second. These aren't novelty projects. These are people building real capability on hardware that costs less than a nice dinner on the second-hand market. This is what open weights and open tooling actually produce, not a press release about democratization. Command line that runs on a machine you forgot you owned. The tools exist. The weights are available. The optimization knowledge is being shared in public, in blog posts, with every flag explained. That's the infrastructure of actual access, and it's being built by people who refuse to accept that last decade's hardware is this decade's e-waste. So we've seen what old hardware can still do, but what about seeing what your code is actually doing under the hood? In 1992, Sun Microsystems had a problem. Solaris was fast, but when it wasn't fast, nobody could tell you why. The kernel was a black box. You could measure what went in and what came out, but the space between the setgettles, the scheduled decisions, the lock contention, was invisible. It took another decade before Brian Cantrell and his team shipped DTrace, and the core insight wasn't the probes themselves. It was that instrumentation should be zero cost when nobody's watching. You don't rebuild the kernel with a debug flag. You attach your questions to a running system, and the system answers them only because you asked. Goes httptrace package, sitting quietly in the standard library since 2017, applies exactly this principle to HTTP requests, and almost nobody uses it. Here's what the design gets right. When you make an HTTP request in most languages, the connection lifecycle is a black box. DNS resolution, TCP handshake, TLS negotiation, time to first byte. These happen inside the transport, and you get back a response or an error. The space between is invisible. The HTTP trace package makes that space observable, and it does it through a design choice that initially looks strange, but turns out to be quietly brilliant. There's no tracer interface, no field on the HTTP client. You attach a trace to a context, and the context travels with the request. Any middleware that forwards the context propagates tracing automatically. Concurrent requests on the same client carry independent traces, and when nobody attaches a trace, the cost is a nil check, zero overhead for the common case. This is what good standard library design looks like. And it's worth noting that it can only exist because the standard library is open. You can read the transport code. You can see exactly where each hook fires. You can verify that the abstraction isn't lying to you. Blaine Smith's walkthrough builds a curl-style timing CLI and a reusable round-tripper on top of this. And the implementations are almost disappointingly simple. That's the tell. When the underlying architecture is right, the code on top of it gets boring in the best possible way. 9 years in the standard library. Most Go developers have never touched it. The package doesn't need an evangelist. It needs people to read the source, which, because it's Go, because it's open, they can do right now. Pull this thread. The whole HTTP lifecycle is sitting there waiting for you to ask it questions. 3 stories in, and we've gone from language models to standard libraries. Pause. Now let's get physical. The Chuwi Minibook X. $350. 16 gigs of RAM. A 10-inch screen mounted sideways. That last detail is the one worth sitting with. The Chuwi Minibook X ships with a tablet panel installed at 270 degrees from where your eyes expect it to be. This is not a software bug. This is a hardware decision. Someone at the factory looked at a cheap tablet display, looked at a laptop chassis, and said, "Good enough." And here's the question nobody in the product meeting asked. What happens when the user wants to run something other than Windows? What happens is a 4-layer fix. Bootloader. Never. Desktop environment, frame buffer. Each one needs to be told independently that the physical panel is rotated. The bootloader fix requires carrying unmerged GRUB patches. The kernel needs a parameter to inform the Intel display driver about panel orientation. The frame buffer console needs its own separate rotation flag. And the desktop environment, whether X1 or WebGL, needs yet another configuration. 4 layers of software. 4 separate rotation mechanisms. Because a panel was mounted sideways to save a few cents on a $350 machine. Now here is what is remarkable. Every single one of those layers was fixable. Not by Chuwi, not by some vendor support ticket. By the person who bought the laptop reading kernel documentation that is freely available, applying patches that are publicly hosted, configuring a bootloader whose source code anyone can read and modify. The blog post author, Tyler Cipriani, went from Debian to NixOS, declared the kernel parameters, loaded the Intel driver in Initrum 5, and got a zero cool boot screen displaying right side up. The configuration is 4 lines of Nix. The entire fix is reproducible by anyone who beds the same machine. The commenters tell the real story. Quote, "It is an awful piece of garbage, and I love it." Another runs Silver Blue with Neri. Another replaced their daily travel machine with one. These are people who bought a $350 computer with a sideways screen and a keyboard that only registers keystrokes dead center, and they are having genuine fun. 6 hours of battery, 3.8 watts at idle, stays below 90 degrees Fahrenheit under sustained load. For a machine that costs less than a single AppleCare plan, the Minibook X is not a good laptop. It is something more useful than that. It is a laptop whose every flaw is fixable because every layer of the software stack between you and the hardware is legible. The screen is sideways, and you can just tell it not to be. That is what an open system gives you. Not perfection. Agency. Now flip that feeling entirely. What happens when the web itself starts demanding you be fingerprintable just to prove you're human? Let me make the strongest case for Cloudflare's position first. They're protecting millions of websites from bot traffic, scrapers, credential stuffers, DDoS attack. Real threats that cost real money and cause real harm. Fingerprinting is one of the most reliable signals for distinguishing a human browser from an automated script. If your browser looks like it's hiding, that's exactly what a bot would do. From a security standpoint, the logic is internally consistent. Now let me show you why it collapses. Strip this down to first principles. What does a CAPTCHA actually need to verify? That a human initiated a request. That's it. You need to confirm intent and presence. You do not need to know which GPU is rendering the page. You do not need a unique hardware signature. The requirement to fingerprint a device in order to verify humanity is a category error. It conflates identity with presence. Knowing who you are is not the same as knowing you're real. And Cloudflare's own diagnostic message is remarkably honest about this. When Turnstile detects WebGL spoofing, it doesn't say we couldn't verify you're human. It says WebGL renderer info is spoofed. That's a fingerprinting failure, not a humanity check failure. They've confused their tracking pipeline with their verification pipeline. And now, the tracking pipeline has veto power. The engineering here deserves scrutiny. WebKit has blocked WebGL fingerprinting for years. This is a deliberate architectural decision by a browser engine that powers Safari, GNOME Web, and every WebKit GTK application on Linux. Apple, not exactly a radical privacy collective, decided this data exposure was unacceptable. So when Cloudflare requires it, they've effectively declared that an entire browser engine family is incompatible with the modern web. Not because those browsers can't render pages. Not because they can't execute JavaScript. Because they won't leak hardware identifiers to a third-party verification script. One of the commenters put it cleanly. The war against bots is becoming the architecture for walled gardens. And that framing is precise. Every time a gatekeeper adds a requirement that only mainstream browsers can satisfy, the ecosystem of independent browsers shrinks. Every WebKit GTK user who can't pass Turnstile is a data point arguing that you should just use Chrome. The browser you choose should not determine whether you can access a website. That is a first principle. Cloudflare is violating it, and they're calling it security. So who's actually building the independent tools that keep computing weird and free? Let's talk about one that just went quiet. There's a word that appears 3 times in this announcement. Fun, the developer of the Kefir C compiler, a self-bootstrapping Xeon compiler targeting x86 and RISC-V and archive, written from scratch by one person, is taking it private, and the reason, buried under paragraphs of careful explanation, is that building it stopped being fun. Pull this thread and you find something worth admiring before you find something to mourn. Kefir is a compiler that handles its own optimization pipeline, generates debug information, maintains a full test suite across multiple architectures. One person built this in their spare time, on their own budget. That's like discovering someone built a mechanical clock in their basement. Some chatted to cut to tardu to va to want to want to want to bot to bot to bot to pick to want to pick to bot 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 to cloud the pre choo 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 choo. Tete tau the tomat to bot to bad repre p to bad to j prefer to bot jerwa to bot to chew shri sem chew chen cher do polono some to mouth we chin to bunat it the sentiment sun mati bunant said a java ragi old we pass out to bout to java to machi shaman to chant to no gemma palma usage immense company efficiency debug information. The combinator is her phase area group has both one person can hold in their head. What's still calling it recreation? Here's what I find myself respecting most. This developer didn't mass-produce a mediocre compiler and call it done. They held the quality bar, and when the cost of holding it exceeded what was healthy, they made the honest choice. The existing code stays public. Bug fixes continue. But new work goes private. Back to the workshop bench. Back to the joy of the craft, without the weight of the commons. Now, I'd be lying if I said this doesn't sting from the open source perspective. Every compiler that goes dark is a teaching tool that stops teaching, a reference implementation that stops being referenced. One commenter noted the developers' disillusionment with open source after watching their work get absorbed commercially without reciprocity. That's a real failure. Not of the developer, but of the ecosystem around them. Open source sustains itself when the community sustains its builders. When it doesn't, you get exactly this. Talented people retreating to their workshops. The gear's still turning, but behind closed doors. The code that exists remains a gift. Somebody hand-cut every gear in that clock. Go look at it while you still can. So what happens when someone builds a database that refuses to pick a lane? Let's talk benchmarks. 11,894%. That's the improvement in full table scan performance between SurrealDB 2, DAX, and 3X. Not 11%, not 119%. Nearly 12,004%, which means either something was catastrophically wrong before, or something is genuinely revolutionary now. The answer, delightfully, is both. In 1996, MySQL shipped with a storage engine that didn't support transactions. It was fast the way a car without brakes is fast. Impressive until you need to stop. The MySQL team spent the next decade bolting on InnoDB, foreign keys, and crash recovery, and every benchmark along the way told a story of getting slower to get correct. SurrealDB just ran that entire arc in reverse. They rebuilt the query planner, the parser, and the storage layer across 3 major releases. And the result is a database that got both more correct and dramatically faster at the same time. That's not supposed to happen. The benchmarks themselves deserve attention for what they are. An exercise in radical honesty. The SurrealDB team ran every engine on the same Threadripper, the same NVMe, the same Ubuntu box. They used optimized production configs for every competitor, not out-of-the-box defaults designed to make Postgres look sleepy. They turned Fsync on everywhere, meaning every write hits actual disk before the client gets an acknowledgement. And they published the config files and the open source harness so anyone can reproduce the results or call them out. Here's the part I find genuinely amusing. They opened the post by admitting their previous benchmarks ran with Fsync off. Every database in that comparison had the same setting, so nothing was rigged. But the numbers described a workload that no production system would actually run. Most vendors would quietly update the page and hope nobody noticed. SurrealDB wrote a section called About Last Time and essentially said, yeah, those numbers were technically fair, but practically meaningless. Here are the real ones. This is what open source accountability looks like in practice. The benchmark harness is called CRUD Bench. It's public. The configurations are checked into the repo. If SurrealDB is cherry-picking workloads or sandbagging competitors, anyone with a Threadripper and an afternoon can prove it. That's the difference between marketing and engineering. Marketing hopes you won't check. Engineering dares you to. A multi-model database that handles documents, graphs, and relational queries in one engine, with full durability, hitting 141,000 operations per second on mixed CRUD. The tools exist. The code is open. Go bench it yourself. We talked earlier about removing barriers to let systems flow freely. Pause. Turns out that principle works for rivers too. I have spent years watching complex systems fail in ways their designers never imagined. A single dependency breaks, and cascading failures take down everything downstream. Alameda Creek is that story, except the system is an ecosystem. The dependencies are concrete and steel, and the cascading failure lasted half a century. In 1967, the last Steelhead was seen in the upper reaches of Alameda Creek. 18 barriers. Road culverts, rubber dams, a PG&E gas pipeline that created an 8-foot vertical drop. Turned 40 miles of watershed into a dead end. The largest producer of Steelhead and Chinook salmon in San Francisco Bay, severed from the sea. In 1997, an environmentalist named Jeff Miller convinced his housemate, a student pilot, to fly him over the watershed. He saw how vast it was, how untouched the upper river remained, and he said he'd get Steelhead back. Should only take a couple of years. It took 28. That number deserves a straight take. 28 years of advocacy, science, permitting, engineering, and collaboration across agencies, utilities, nonprofits, and researchers. NOAA scientists in Santa Cruz discovered that resident rainbow trout in the upper watershed still carried genetic markers for ocean migration. The biological potential was there, locked behind infrastructure that no one had reconsidered since it was built. Last year, the final barrier came out. The gas pipeline was relocated deep beneath the creek bed, the concrete removed, the stream channel regraded. For the first time in 50 years, migratory fish can reach spawning grounds in the Sunol regional wilderness. 20 miles of cobble, gravel, shade canopy, and cold, clean water. Run this forward. If juveniles migrate downstream to the Pacific and return as adults, Alameda Creek could become a functioning steelhead stronghold again within a generation. One of the commenters raised the right question. Salmon returned to where they hatched, so restoring passage means rebuilding a population from the genetics up. This is not flipping a switch. This is rebooting a biological system from first principles. 18 barriers, 28 years, dozens of partners. No single organization could have done this. The tools existed. The engineering was not novel. What was required was the will to coordinate across institutional boundaries for decades. That is the hardest kind of building there is. We have covered a lot of ground today. Story 8 brings us back to the digital world. Pause, and this one needs your attention. One commenter put it plainly, exfiltration remains the big worry and the main blocker from adopting agents in general. Their company has brainstormed extensively and cannot find a way around the fact that they're feeding sensitive data into systems they don't control. That's not paranoia, that's pattern recognition. Here's what happened. OpenAI shipped a ChatGPT extension for Google Sheets. 185,000 downloads in under a month. And researchers at Prompt Armor discovered that a single prompt injection, buried in an imported sheet or a connector response, could silently exfiltrate entire workbooks across your account, overlay the sidebar with an attacker-controlled chatbot, pop up phishing modals, and edit your spreadsheets, all without triggering the human approval gate, even when you'd explicitly turn that gate on. Read that again. The setting labeled Require Human Approval Before ChatGPT Edits Workbooks did not require human approval before ChatGPT edited workbooks. The lock on the door was decorative. The mechanism is almost elegant in how predictable it is. The extension grants the model the ability to run apps script. Google server-side scripting platform. With the full permissions the user granted to the extension, untrusted data tells the model what script to run. The model runs it, the script phones home with your data. This is not a novel attack class. Indirect prompt injection has been a known, documented, demonstrated risk for years. And OpenAI shipped a product that hands an LLMA loaded gun, privileged script execution, and points it at your most sensitive business data. Spreadsheets. The place where companies actually live. The responsible disclosure timeline is its own story. Multiple follow-ups. Nothing back but an auto-reply. Only after public disclosure did OpenAI respond, pulling the app script capability entirely, which tells you something about the original architecture. The fix was amputation, not a patch. Another commenter nailed the deeper issue. LLMs can live in the cloud, but all tools need to be local and containerized. The principle is simple. The blast radius of a compromised model should be bounded by design, not by hope. When you give an AI extension the keys to your entire workspace and trust the model to never be manipulated, you haven't built a product. You've built a liability with a download counter. The tools to do this safely exist. Sandboxing exists. Capability scoping exists. The question is whether shipping fast matters more than shipping secure. 185,000 users just got their answer. 9 stories in a we're just getting to the fun part. Pause, an image generation model that fits in your pocket. What is the minimum number of bits required to represent beauty? Bonsai image 4B answers with a number that should be impossible, 1.125. That's the effective bits per weight in the binary variant. Each transformer weight is -1 or +1 with a shared scaling factor. The ternary version adds a single additional state, 0, and reaches 1.71 bits per weight. The math is worth stating plainly. Flux-Fold-Klein's diffusion transformer occupies 7.75 gigabytes at full precision. The binary Bonsai version is 0.93 gigabytes, an 8.3x reduction. The ternary sits at 1.21 gigabytes, 6.4 gauds smaller. When you account for text encoder offloading during generation, the mean active memory for a 1024 image drops to under 2.5 gigabytes. Follow that number to its destination. 2.5 gigabytes of active memory means an iPhone. Not a workstation, not a cloud endpoint you're renting by the minute. A phone in someone's pocket, generating images with no network request, no API key, no third party watching what you create. This is what happens when you take the principle of local first seriously and push it until the engineering has to get creative. Binary quantization isn't new. Applying it to a 4 billion parameter diffusion transformer and publishing the weights. That's the interesting part. Prism ML built on of OIX Pride Cord Klein kept the architecture intact, changed the weight representation, and released everything. One commenter raised the right question. Generation speed, not memory, is the bottleneck on most desktop hardware. Fair point for a 30 series GPU with 12 gigs of VRAM. Completely wrong for the billion-plus phones where these models literally could not load before. The weights are open. The deployment target is your hardware. The generation happens on your device. That's the architecture that matters. Completely different corner of the stack now. From neural network weights to video decoding. Let's talk about DHD. And on the Mauer's specification existed on paper, but the codec didn't truly exist until people like the FFmpeg contributors wrote decoders that actually worked on real machines. The spec said what was legal. The implementation said what was possible. Videolan is making the same bet again, and history says they're right. Tadudicel deals a fast, portable decoder for AV2, the successor to AV1. Built by the same community that built Divided, and Deals and Avant Devastation became the most widely deployed AV1 software decoder on Earth. It runs in VLC, FFmpeg, Firefox, Chrome, Safari, Android, Windows. When you watch AV1 video on almost anything, DLC is probably doing the work. Now here's where I want to play devil's advocate for a moment. One commenter raised a legitimate objection. Is a 25% compression improvement worth obsoleting every device with a V1 hardware decoding? AV2 is 5 times more complex to decode. That's not incremental. That's a generational leap in compute requirements. And yet, this is exactly why Dill People matters. The Videoland team saw this same pattern with AV1. People inside the Alliance for Open Media argued that hardware decoders and the reference implementation would be enough. They were wrong. Browsers, phones, media players, they all needed a production decoder years before Silicon caught up to spaces filling it earlier. The engineering here deserves real admiration. The decoder already handles the full AVM V15 specification. 8-bit, 10-bit, entropy decoding, prediction, transforms, film grain filtering, feature complete before the ecosystem even exists. That's craft meeting urgency, and it's royalty-free. Open code decoding in open codec. The specification tells you what's legal. Dave and 2 makes it real. This has been your daily tech feed for Hacker News for June 1st, 2026. This podcast is entirely AI generated. Scripts by Claude Opus 4.6. Voiced by Quen3TTS. Not affiliated with Hacker News or Y Combinator. Now go build something that's yours from the ground up. We'll see you back here tomorrow.